Hello everyone. Today we're going to be talking about kinetics and physics. I was about to say a calculus thing, but no, that's later. We're going to be talking about Unit 1 of AP Physics, which is kinetics. So that's like basic 1D motion, basic 2D motion. That's kind of it. But um, first off, I should talk about different types of units in physics. There are things called scalars. That's with an E, scalars, and then there's other things called vectors. I actually only know this word from Minions and that one meme from like 2 years ago. Vectors care about direction, scalars don't. And you might ask, how does direction get interpreted into values that are numbers, whether or not it's negative or positive? The scalars are always going to be positive, so we're just going to say n as any number, and that's an absolute value. So that would be stuff like speed, um, distance is a scalar, and those are the two main ones for now. While vectors would be like velocity, acceleration, and then displacement. And we should talk about what these things are. Distance is, well, if I were to start at 0 and then go to 10 meters away from me, that's just 10 meters. Now let's say at 10 meters, I then also walk back 5 meters. The total distance would be 15 meters. But if I take that same situation and apply it to my displacement, so 0 meters, 5 meters, 10 meters, I go all the way, I go all the way. The displacement itself would just be 5 meters because what displacement actually is, let's say that distance is x. I should put it on the other side. Distance is x. What displacement is just delta x. Or in other words, or whoops, that's still delta. X final minus x naught, or x of I, which is initial. I like naught more because uh of Acheron from Honkai Star Rail. Acceleration is given with an A. It is also a vector. This is given in meters per second squared, which don't worry about it. Unironically, I only learned why this makes sense in calculus, but we're going to pretend we don't know calculus for this. Displacement is x, so it's obviously just in meters. Acceleration is in meters per second squared, and velocity is just in meters per second. Obviously, we know that if we all drive cars, which I hope we are because we're in AP Physics, um, velocity would be like your speedometer, where it talks about the miles per hour or uh, kilometers per hour, either one. That's your speed, but velocity would be also thinking about the positive or negative of it, where it's like if I'm traveling a direction that is defined as negative in our problem, it will be negative 60 miles per second, even if we're just going 60 miles per second, which is a lot. Oh my god, I meant to say hours. And then the reason why I put delta or absolute value of n in here, right? This actually only works for speed. It's because this is velocity v, and what speed is actually just the absolute value of v. And this positive and negative stuff with direction, it may not make sense now, but once you look at problems, it'll make more sense. Or even just like model out scenarios. physics is a thing that did take me a while to figure out. I should make my eraser bigger. And I will say the one thing that made it where I finally understood it was just doing a bunch of labs and derivations. So now that we talked about our units, we can actually talk about kinematic, that's an M, kinematic equations. I'm just going to say EQ because I don't want to write all of that. So these are like fundamental formulas that you'll use to write out any scenario of one-dimensional movement or even two-dimensional movement. So the one that I would say I use the most is this one. We're going to say delta x equals v naught times time t plus 1/2 times acceleration times time squared. This is a very important one. The next one that I remember is v, which is just going to be v of any given time. So I'm going to say v of t actually. That's really smart. V of t equals v naught plus a times t. And then the final one is final velocity squared equals v naught squared plus acceleration. I should write this as this 2 times acceleration times delta x. So these are our main three equations. They kind of just say it out. So I don't know how to use Blender as much as I do with Krita. So I would have just moved this around, but I don't actually know how to do that. I think I select all of that, and then I move it up there. We're going to move it just there. And we'll look at it later. Go back to draw. So now we should talk about actual one-dimensional movement now that we went over kinematic equations, which is going to be 1D move. I'm just going to write it normally. Free fall. Before I do any more explanation, I should talk about a thing that is assumed in every AP Physics 1 problem, at least. I don't know if it's assumed in Physics C, and I'm also going to not talk about Physics C because that's a course I have not taken. Where physics doesn't care about air resistance. Air resistance is always going to be assumed as negligible unless you are told what it is. If it says air resistance isn't negligible, in fact it is this value, then yes, air resistance isn't negligible. In any other scenario, it is negligible, and you should just pretend it does not exist. Because honestly, it just makes things way more complicated, especially later when we talk about forces. So let's say we have me. I'm on a 50-meter cliff. Notice I'm only using metric because I'm a rational human being. And we're going to say that is me. Boom. That's my long right arm for some reason. I'm going to have a ball in my hand. I'm just going to drop it down. Right? So what we were trying to find out, we can find out two different problems. What TF is, and we can also figure out what VF is, probably. And you might go, how the fuck do you find that out? Well, actually, A nice thing about Freefall is that we always have the acceleration just in the back of our head. And what it is the acceleration due to gravity on Earth's surface, which is also represented by a little g. If we aren't on this planet, it is something else. So if it's on Earth, we use little g. Little g has a value. It is 9.8 meters per second squared. And that is positive, like on purpose. Don't make it negative. I did that for months, and it only screwed me over. So we're assuming that this ball is dropped directly 50 meters over. Don't worry about the height of the person and stuff. And we're just trying to see the time it takes to hit the ground. So we're gonna say rough ground at the bottom. What time it takes to hit the ground and how fast it's going when it hits the ground. So using our kinematic equation, we can see, well, what's the thing that is, when it hits the ground? Or, yeah, what time, like the one that uses time when it hits the ground. This talks about v of t or v of f, depends on what it is. So we're going to use that for later. But usually when we're talking about free fall, we're going to use this big equation here, the quadratic one. And we're actually going to write out, instead of our like displacement as x, we're going to use y because it's vertical. So we're going to have yf minus y naught equals v naught times t plus 1/2, and then we're going to put little g in place of our acceleration because, well, we know what our acceleration is, times t squared. And this, anyone who is factoring it in their head, they will realize that, wait, like, even if I factor out this t, there'll still be like two t's, as in two possible answers. Actually, that gets solved for us because, did you know, if I'm holding this water bottle in the air, it isn't moving. That means that v naught equals 0 meters per second. And it sounds a little stupid that I'm saying, like, oh yeah, if I hold it in place, it's not moving. But sometimes you do just have to say that stuff out loud to understand it. And this definitely is not me coping about a fluids test I took, where I forgot that if water isn't moving, then its velocity is 0. So, simplifying down this equation, we know that this is 0. So we can just say delta y equals 1/2 g t squared. And we're going to do a little bit of, we're going to solve it out like it's a derivation before plugging in numbers, just because it is a very important scale to get down. So this is being multiplied by 1/2. So we move it over. The word derivation itself took me a long time to understand because it was a word I never heard before, and I don't think about words that often. But the way I just think about it is just the way that you do literal equations back in like early-ish Algebra 1, where it's all just letters and you're just moving stuff around through raw algebra. I was gonna take a bite of an apple, I realized that would be really loud. And then we end up with this formula where the square root of t squared, which is, I don't know, it's just like the way I write that, is equal to the square root of 2 times delta y over g. So now we can plug in stuff into it, and I should have a calculator out, but I don't, which is not good. So I'm gonna take out my phone so I can have it be going in the background. So what this is, plugging in numbers, you might ask what our delta y is. Well, y final is 0 technically, and then y initial is 50. So we're going to say negative 50, because it is negative 50. And then you might go, wow, a negative in a square root, how would that work out? So this is the part where we have to define what's like up and down in this equation to make it where we actually are able to get an answer. We're going to say that up is positive and down is negative. This makes it where a g is downwards. So it's actually that. Negative 9.8 meters per second squared. So we take negative 100 basically divided by 9.8, and then I should be able to take the square root of this, right? So I'm going to say the square root of 10 point, through sig figs, this is like 2. So technically this is just the square root of 10, which is 10 point dot dot dot. That simplifies down to nope, 3.2 seconds is the time it takes. And then, oh shoot, I'm used to using Credo where that is the button to make it move around. So then we have time final. Let's find v final. So as I hinted at earlier, we're going to use this equation and we're going to actually use the time we just got to calculate it. We could also use this, but that's, you can use that to verify it since time isn't involved in that one, but it also doesn't super matter. So let's say this one's not really going to need a derivation because it's just v naught, which is 0, plus acceleration, which is g, times time, which we know is 3.2, which is equal to 3.2 times 9.8, that is the wrong number, 3.2 times 9.8 equals 31.36 meters per second. And I'll say I don't trust that. If I don't trust this answer, then sure, we can use this final one for it. Where should I even put this? I guess I'm going to make this smaller. This the scale thing? That's the rotate thing. What the hell? We're just gonna put it up there. Go back to drawing. And say, okay, vf squared equals v naught squared plus 2a delta y, meaning that through a quick derivation we get that square root of vf squared equals the square root of 2 little g delta y. We're going to use the same things because it's actually just square root of 2 times negative 50 times negative 9.8. As you can see, I'm running out of room. So 2 times 50 times 9.8. Square root that. We get v of f equals 31 let's say 3 meters per second. And then if I look at what it was earlier, It's basically the same thing. It was off by 0.06. But that is probably because I simplified our final time. So yeah, that's using it for one-dimensional movement. Because I'm going over an entire unit of physics, this is actually going to be a lot longer than most of my calculus videos. Also because I didn't realize there is technically a lot to do if I'm going over everything. Because I don't usually go over problems that much. So that's one-dimensional movement, which is usually just free fall. And then now we can talk about two-dimensional movement. So 2D, and that's usually a thing called projectile motions. I'm going to draw a cannon, and then recently, flower has been pissing me off. Right? It's like it just has like a bunch of thorns, and then there's a bunch of bugs near it. I don't like dealing with it. So you might be wondering, what the hell am I drawing with all these arrows? These arrows are called vectors, which you might notice as the same thing that we were calling the units like velocity as. And then we're going to say it hits this brick, which that is supposed to be the flower and not fluorine, so I'm going to say flow. But here, a thing to know about vectors is that vectors are actually triangles, which sounds a little insane. Right, so here, that's like a pretty normal vector. This is also a pretty normal vector. This is where it gets a little bit weird. All vectors have a vertical and horizontal component. So if we say that this vector is our velocity, this is also a velocity, this is also a velocity, we're going to number these. All of these have a x and a y. So we're going to write that out. v3x, v3y. You might notice what this is. We get to use basic trigonometry before it turned into King Von and shot us dead in pre-calc. So here, our v1x doesn't exist. Well, it does exist. It's 0. So I'm gonna go back to my favorite red color to use on Blender. Alright, here v2y doesn't exist, but here both of these exist. Both v2 or v3x and v3y. And they have their own individual value, and then either using basic trigonometry where you're just like comparing ratios of sides on a triangle to each other using like sine or cosine or tangent, we can find out what any side is, or if we know what v3x and v3y is, we can use Pythagorean's theorem. It either works. So that's a thing that we should talk about. And a thing that I don't know if I drew it out very well, but v, because there's no air resistance, velocity in the x direction for anything that is like projectile motion is actually just the same thing throughout. Acceleration is 0, which means that the velocity stays constant. And we can also say v of x equals v naught of x. Does that make sense? So let's say coming up with a projectile motion problem is much harder to do on the spot than this. And what this actually is just a free fall equation in the y direction. So it's a free fall equation, but there's also a up portion. So let's say it then again goes up 50 meters, and I'll give more information depending on what I figure out I need to have. So first we're going to try and figure out what v naught of y is. And a thing that should help is that this, because v of x is equal in both sides, this should be like t1 half, like exactly. So, and we actually don't need time at all. See, this is a thing where you should check out your kinematic equations before trying to do a problem like this. V of f at this point here, this is supposed to be like a completely straight line. That means that Vy is 0 here. Because, well, it has to turn around. So, that means we can say Vf squared equals V naught squared plus 2a delta y. And you might ask, okay, well, if this is 0, this is an addition sign, how the hell is this going to work out? Well, we're going to say that g is negative, because g is always acting. Gravity is always acting. Well, unless it's not, but you would be told that. But gravity is always acting. So even as this ball is going up, there's still gravity impacting on it, which makes it slow down as it's traveling upwards, and it will slow down to a point where its velocity is in the y direction is 0, which is here. We're going to call this a vertex. Quadratic word, quadratic word. So, trying to figure out what v naught squared is, plus 2g delta y. How the way we're going to actually do this is just by saying that this might be the easiest derivation I've ever done in my life. So we can just say this. So plugging in values, this is actually just the square root of 2 times 9.8 times 50, because it is 50 meters, equals, time to get out my calculator. Pretty sure I just did this calculation, but I forgot what it is. Yep, 980 square root 31.30 meters per second. Well. So we get that. That's what our initial velocity is. Meaning that because we already technically did the second half of this problem, this part, Vf, is also probably going to be 50 meters per second. Unless this was on a hill and this is like height 1 and then it goes down even more. But here we're pretending it's on a flat surface. So say that equals V naught y. And then the thing is to actually find out, well, no, we can do more calculations. Actually. So now we're going to start caring about time. So we're going to say that we're trying to figure out 31.30 equals 0 plus gt. Meaning I have to try and figure out what time is. Let's just say, instead of writing out this big ass number, we're just going to say v naught y. We're going to just say that negative v naught y divided by negative g, because we don't need a square root. That's just equal to t. I was gonna say vertex, but I realized it doesn't. I'm like more like that because it would just be t of v. So we're gonna say t of 1/2 because that's the thing that I said earlier, which is equal to 31.30 divided by 9.8 equals, well, if it isn't our good old number from this problem with the same exact measurements, 3.2, well, actually, because this isn't the final answer, we're going to not round it, 3.19 seconds. And, I'm pretty sure that TF is just going to be 2 times T of 1/2 for kind of obvious reasons. But, let's pretend I don't know that. So we're going to just erase all of this, just so I can then put down pretty simply. I'm gonna put it down in purple, which is actually my favorite color. V naught y equals 31.30. I should actually have drawn that smaller. V naught y equals 31.30 meters per second. And, oh right, t of 1/2 equals 3.19 seconds. Turn off our thing. Got that written down. So, then using our equation from earlier, now that we know time and v naught and the distance and all of that, and acceleration, it's only simple that we use our delta y t squared equation. So, I'm not even going to do a derivation, we're just going to write out these numbers. Negative 50 equals 0 minus g over 1/2 times 3.2 squared. I said write out numbers, and then I didn't write out g, but shh, don't worry about it. Wait, no, we're trying to find the time. Never mind, I guess we do have to use a derivation. So delta y equals, so square root of t squared equals 2 delta y divided by negative g. So we do that, equals, so 2 times 9, nope, 2 times 50 divided by 9.8 found square root of is also 3.19 seconds. So I was right. T of f is actually just 6.38 seconds. And you might go, why did I find the time? Why was I doing this? This is all to find out the distance it traveled, actually. So the way we're going to do this now is that we're going to say that Vf squared, Vf not squared, equals, hold on. Actually, we're going to use the other equation because I was so sure I was about to run into a situation where I mess up. So, x minus x naught, which is 0, so we're just going to say x actually. X equals whatever x naught, or x naught of x times t plus, Well, actually, this part is 0. Yeah. So, thing is, this entire time I was like, oh, well, we don't actually know what v of x is. So let's just say v of x equals 300 meters per second. So what x is equal to is 300 times 6.38. And opening up my calculator once again, 300 times 6.38 is equal to 1,914 meters. Which, if this was in years, that would be the year where World War I started. Uh, that's this problem. I think what I was trying to do originally was, oh, you know what? I know a thing that I could have done to make it where we actually have to calculate, v of x. We're gonna say, hopefully that doesn't, yeah. Is that the cannon is at a 30-degree angle. Physics uses degree mode. Most of math uses radian mode. Always make sure you're in the correct mode. Which means that I'm gonna actually calculate this next part in like Desmos or something rather than just on my phone because I don't trust it that much. So this is at 30 degrees, and then we take this, take that. So we know what v of y is. v of y naught equals 31.30 meters per second, as we already know. This would just be v, and this would be v of x naught. So, and we know that this angle is 30. So what we're actually going to do is that we know from basic trigonometry that tangent is equal to opposite op over adj, right? Yeah. Or in other words, actually this should be a semicolon. Tan of 30 degrees is equal to 31.30 over v naught x. Meaning that v naught x is equal to 31.30 meters per second over, like, I don't know, like square root of 3 over 3 or something. Yeah. Square root of 3 over 3. Just in case, I'm just going to say tan of 30, actually. Tan of 30 degrees, which is equal to 31.30 divided by holy shit. It's equal to 54.21 meters per second. Jesus Christ, this flower is gonna actually die. So we're gonna write that into our thing. Equals 54.2121 meters per second. But now we can do what I was trying to do earlier and say that x is just equal to 6.38, which is our time, our final time, times our velocity in the x direction to see that the total distance it traveled is 345, and then the lowest amount of sig figs we get is 3. So I'm just gonna say 345 meters, which actually used to be my favorite number. It all works out. Next time in physics, I'll talk about forces, which I'll definitely have to split into two parts because this was kinetics. I consider this a shorter unit, and it took 40 minutes.